everybody. Thanks for the introduction. It's not my first presentation, but it's the first in the morning. So welcome everybody. I just have to get sorted here a little bit. Oops. I'll do it like this. Perfect. Well, my name is Thomas Weibler, co-founder of Flex Optics and also CTO at Flex Optics. A company is specialized in optical transceivers. And I brought today a topic with me where I think it's quite interesting to see because I get pretty much into details of transceiver technology in these days. And where I'm coming from is that, like this, that like 20 years ago when I started in networking, 100 megabit was somehow commodity. And looking also in the networks in these days, there was some complexity, but it was compared with the networks today, way less complexity. And 1 gigabit 20 years ago was somehow the latest and greatest technology. And comparing it today, where we are now, we are talking 10 gigabit is definitely commodity, 100 gigabit is also commodity, and 400 gigabit is the latest and greatest, which will come up or is already there actually. So in my presentation, I brought you, or I show you here, two types of transceivers. So the first one you're quite familiar with, it's the SFP Plus 10 gigabit, and I open up for you those two types. And the second one is a 400 gigabit QSFP DD. And I don't want to talk about 10 gigabit any longer, but the interesting part is now in the 400 gigabit transceivers, what is inside there. So we got a transmitter and a receiver, the two nice golden boxes which you see there, and also the DSP, the digital signal processor. We heard yesterday also a little bit from Finisar that the DSP has a major function beside the modulation, which is a key component for the DSP. There is also another task for the DSP to take care about forward error correction. So in my talk, I will cover the transmitter and the receiver section and also the forward error correction of the DSP. So let's start with the transmitter. And in optical assembly, this transmitter, this nice golden box, which you see here, is also called a TOSA, transmitter optical subassembly. Now this golden box is quite empty at the current stage, so we have to fill it up. First of all, on the left side, you see an electrical connector which connects the TOSA to the PCB itself, where it brings the high-speed signal in and out of the TOSA, and also feeding either the DSP or the ASIC of the switch directly, depending on the setup. Now, we got the high-speed signal in there, and first of all, we have to convert it. So therefore, we use laser diodes. And as we are talking about 400 gigabit, and this also applies for 100 gigabit technology when it comes to single-mode transmission, or on transmission on single-mode fibers, we need 4 lasers. So each laser is carrying up to 112 gigabaud, and so 4 of them will end up in 450 gigabaud, roughly. And these lasers, what they do, they basically convert from the electrical signal to an optical light level. Now, they have 2 characteristics, basically. First of all, they need current to operate, and they heat up. And the second one is the light which is emitted out of those lasers is, I would say it's blurring out, so it's not focused at all. So we have to take care of these 2 characteristics. So the first one is that we're gonna need a cooler, an electrical cooler, which also takes current to cool down the laser diodes to keep them somehow stabilized. And why is it important to stabilize the lasers? Well, if they're gonna heat up too much or there is a variance in the temperature, the emitting light which is coming out of the lasers will drift away, and that's something definitely what we really want to avoid. We want to have the laser stabilized in wavelength, because when the wavelength is shifting away, this will end up in bit errors, for example, which you see on the interface later on. So that's definitely a major role, having the cooler, a proper cooler in there to keep the laser temperature stable. And the second one, you can imagine if you have non-focused light and you want to focus it, you need lenses, pretty much like people wearing glasses. If they take off the glasses, they don't see anything or don't see properly. So when they put on their glasses in the right spot, then it's in focus. And this right spot is quite important. You have to imagine this golden box has a size and a dimension of 5 by 10 millimeters, the overall box. Now these tiny lenses in there, they have a dimension in XYZ of 0.5 millimeter, pretty small actually. And in production process, you have to place them in XYZ. So this is done with micromechanics in 50 nanometer steps. And then the second challenge happens. You need to fix them there to stay there for the next years and decades during operations. And that's typically done with UV hardening glue. And you can imagine that this glue also needs to be some specific characteristic that it doesn't change its consistency or its behavior. It always needs to keep the lenses in that spot for the lifetime of the transceiver. So now we have focused light and 4 wavelengths, the yellow, red, and the blue and green one. But as you can imagine, getting down there to the receptacle where you plug in your LC connector to hit the fiber, we need an additional component to get it there. That's typically done with an optical multiplexer. You might be familiar with multiplexers. You know them as a 1U chassis, either carrying 8 channels or 20 channels in DWDM or even beyond. Now this one is a really tiny one, a really tiny filter block doing 4 channels. How does this work? It's pretty much physics based on what we know from a mirror. So we have dotted glass at the end or at the edge here, and at this edge, and the light is reflecting with an angle a little bit, and then it happens that we get the zigzag down there to that spot. And this happens or applies to all 4 colors. All 4 colors are combined in within that filter block, and the signal is bouncing back and forward always at the dotted glass at the end of, or at the edge of the filter block. So now we are at the filter block, getting out on the receptacle on our fiber, and now the signal is on the fiber, and we have to hit the receiver. The receiver pretty much looks the same. And this time it's a gray box, not a golden box any longer, but the color doesn't matter here. So we got the 4 wavelength inside that gray box now, and what we have to do now, pretty much the opposite. So first of all, we need a demultiplexer to separate all the 4 wavelengths again. So we undo basically the zigzag with the speciality that at the end of the filter block, or at each section, we have a filter actually, and this filter works like sunglasses, so it only allows a certain wavelengths to pass and the others are going to be reflected. And that's happened here actually. So the green light at the green filter is passed through, and the other colors are going to be reflected backwards and bouncing back and forward again until it hits the proper filter, and then it's going to be released out of that filter block. So now we have 4 separate wavelengths again, and they hit a lens again to get focused. As I said, opposite way, we need focused light again, and then we have a pin diode there. This pin diode does the optical to electrical conversion, so we get now an electrical signal out of those pin diodes. These pin diodes, or this electrical signal, has a certain characteristic. It has a really, really low amplitude. So the post-processing systems like the DSP or the AC control switch, they can't handle that signal because the strength is too low, the amplitude is too low. So like at home, when you listen to music and it's too quiet and you want to boost up the music, you need an amplification, you need an amplifier. The same we do in the ROSA here. And it looks like this. It's an electronic component, has an input, takes the electrical signal, takes current again, and gonna boost up the input signal to the output that the post-processing system can handle that signal. One side story here is you might have faced that situation when you have installed a 10 gigabit link of, let's say, 60, 70 kilometers with a very extended reach transceiver. And this works typically. And if you did this in the lab and you connected these type of transceivers for this very, very long reach back to back without any attenuation, you might have identified a behavior like, oh, the link is coming up, it stays there for 5 seconds and then it drops and then it never comes up again. So actually what you have done there and what people think they have burned or broken the receiver or the diode, actually you haven't broken the diode is still alive, but you have burned the amplifier because the amplifier got way too much current on the input and boosted up that signal way too much and basically destroyed himself due to the fact that the input signal was too high. So you can fix that if you change the amplifier in that tiny part, but you need really smooth or really not shaky hands actually to do so because it's really small. So when it comes to production of these parts, especially also in the optical transceiver field, there could be a lot of things to cover and to talk about, and this would definitely extend this talk now. But I want to point out one important thing where I think is quite important to see and to know. It's about the timing. What I did here for you is I put on that diagram on the x-axis we have, let's say, the 3 generations of transceivers like 10 gig, 100, and 400 gig. And on the y-axis, it's the timing in minutes. We have 3 graphs. The blue one is the assembly time. The green one is the testing time. And the orange one is the combination of both of them. And looking at a 10 gigabit transceiver, we are talking about roughly 8 minutes to do production and also testing. For sure, it's normalized because this is done in batches. But overall 8 minutes. Looking now on that road towards 400 gigabit, just for the assembly we are there at roughly 25 minutes to assemble the overall part. But there is some, yes, there is some complexity to build those components, and so yes, it makes sense that this takes a little bit longer comparing to the 10 gigabit ones. But the interesting rise which you see here is the testing. Testing has a way steeper rise going up to 90 minutes of a 400 gigabit transceiver to do testing there. And the overall combination is then roughly 115, 120 minutes then. And I think that's something really important to see because testing, or let's say the other way, is if you want to save costs on a transceiver part, you better don't do this on the assembly because there is not much margin, but you can do this on the testing because there's a lot of margin there to save costs because time is money, and when you cut down the timing, you save money. Having test equipment, which is quite expensive, and if you occupy it too long, this costs at the end of the day. Now, there are 2 ways to optimize. There's a good way to optimize it when you do automated testing there, and there is a bad way if you're going to get rid of test cases. In both circumstances, you will cut down the timing, but this will also end up either in keeping the same quality when you do it more automated, or if you cut down test cases and remove them, then this will end up in a weak quality or having more failure parts at the end of the day. I pointed out one example for you to give you a rough idea about test cases, and I took the example of temperature here. So here on the left side, you see my artificial Tosa and Rosa on 0 degrees centigrade and also at 70 degrees centigrade. So one test case could be when we just take the temperature as a variable here. We cool down the laser to 0 degrees and measure the performance. We figure out, well, one laser is drifting a little bit, and we wait until this laser is stabilized again. And then we say, well, check. And then we boost it up to 70 degrees centigrade, or heat it up actually, and do the same measurement, wait, and until it's stabilized. The part has passed the test. Now, if you're gonna add, instead of having temperature, we also add the time to that test case, it will look totally different. So we start at room temperature, cool it down within 30 seconds to 0 degrees, and allow the transceiver within, let's say, another 30 seconds to get stabilized, the wavelength, and then heat it up to 70 degrees within 60 seconds, and then also do the measurement and give the transceiver only 30 seconds to stabilize. Then, most probably, in the first test case, the part which has passed might fail now because it takes too long to stabilize. Here you can see the difference when you add more variables to a test case, that you get way more valuable information out of it, which ends up in a, yeah, let's say, better quality, or in terms of a more reliable product at the end of the day. Excuse me. So, let's take another real-world example, which might give you a rough idea where what I'm talking about. Is I have this artificial crane here. So it's this horse is spinning that wheel, and the gear here is lifting up that weight. So far, so good. This works. When the horse is spinning, the weight goes up. Now, if even the tiniest gear or wheel in that gear will break, the overall system won't work any longer. And it could be even worse, that this has some influence on other components like the weight, which might destroy something else. And the same can happen in a transceiver. If one component, even the tiniest component, will fail, it can destroy or influence other components. So, for sure, at the end of the day, the goal is to get a green light at the production, and this in a very time-efficient manner. And the key thing here is automation in a really high level of the overall process, especially when it comes to testing. At the beginning, I also introduced the DSP with that function of the forward error correction. So this is now the third part I want to talk. The forward error correction inside of that DSP is needed since, when it comes to Ethernet, since 100 gigabit and also for 400 gigabit. Before that, in 10 gigabit or even 1 gigabit, we had only error detection. And when you look into your Ethernet frame, at the end of the frame, there is this 4-byte cycling redundancy check. That's basically done to detect errors in the frame. Now, this is not sufficient any longer for 100 gigabit and 400 gigabit. We need, instead of only having detection, we also need a correction. How does this work? Typically, the forward error correction is done on the switch itself when it comes to 100 gigabit links. So the FEC basically encodes the stream, brings it, here is somewhere the transceiver brings it on the line, and then hands it over, the transceiver hands it over to the switch, and there is the decoding done, and also the error are corrected. I took a real-world example here with a lorry having some payload and an excavator. So my lorry here is basically the FEC encoder, and the payload, which is, let's say, our Ethernet frame of 1,500 bytes. These are our bricks up there. So in the second step, the lorry hits the road, the dodgy road, the bricks are disordered somehow, and it's even one is falling off. And on the third stage, on the receiving side actually, the excavator is the FEC decoder, and he brings all the bricks back in order that it's going to be handled from the post-processing systems like the ASICs. Now you can imagine that this excavator, he takes a little bit time to get all the bricks sorted, and that the same applies to a forward error correction. In Ethernet, we are talking about, when we do detection and correction, of 100 nanoseconds delay, which is added by the forward error correction. In a 100 gigabit link, this is not so critical, because in some applications there is no need for the forward error correction. I will come there later on. But in general, when you have the FEC in place, keep in mind you will have delay on your link. Now, how powerful is such a FEC? This is also quite interesting to see. When we take those 1,500 bytes, these are, when we do our math, this is 12,000 bits. When the errors are equally distributed all over that frame, we can correct roughly 330 bits. And when the errors are clustered at a certain spot, then the performance gets really down to roughly 33 bits, which we can correct. So now you get a rough idea how powerful it is. In 400 gigabit, it looks quite different, and it's getting more complex there. So we still have the forward error correction on the switch, but now this is actually FEC 2. It does the encoding, and now on the transceiver we also have a forward error correction. That's the one inside the DSP. And it does the decoding actually. So on the communication between the switch, between the switch and the transceiver. the signal is passed over to the FAC1, where the encoding is done again, and passed over on the fiber, and on the other side, it works vice versa. FAC1 decodes, and then FAC2 encodes it or hands over to the switch. So now we have 4 FACs in place in the overall link, so we had more delay. And yeah, I think that's important to know. Now, when it comes to practical attempts in the field, you might have identified when you build up 100 gigabit links that you have bit errors on the link itself. And that's the point where you have to check the settings of the FAC, if it's enabled or disabled. Typically, this should be done automatically based on the type of transceiver which is plugged in or the technology. So let's say an SR4, a multimode-based one, or a CWDM4 transceiver, the FAC should be enabled by default, and that's done by the operating system. While when you plug in an LR4, the FAC is not enabled. And I have seen implementations where the FAC wasn't enabled at all, and then this ended up, like, let's say, on a multimode SR4 transmission, ended up in bit errors. So double check the settings there when it's not enabled, enable it by default, enable it by manual, and you might see that the bit errors will disappear on your link. And the second one, which can also happen, is when you have an unequal amount of FACs. So when you have either 1 FAC in place or 3 FACs later on at 400 gigabit, this won't work at all. It's like the Bobby car here. It's way too big for the excavator to handle it, and this doesn't work. And I think this is really important to know, to double check the FAC settings then when the link doesn't come up. And also, you can imagine now you have 4 FACs now for 400 gigabit. You need to know which one is enabled and which one is not enabled. So either 0, 2, or 4. Yeah, I always do at the end of a presentation quite a summary where what we are seeing currently when it comes to real world. So this was quite a lot of theory, but when it comes to practice, what is currently doable in transceiver technology, I pointed out 3 basic things I see currently in 2019 and also for 2020. 400 gigabit LR4 is an interesting topic to talk about because it's not standardized yet. The standardization on Ethernet is mainly done by IEEE. And LR4, from the idea is we have a single mode transmission within a 1310 nanometer window and up to 10 kilometers. Now, IEEE and the industry who is building the transceivers are not haven't sorted it actually on which wavelength grid they will go to. Either they will jump to the LAN WDM, which is well known from 100 gigabit LR4, 5 nanometer spacing of each wavelength, or we're going to jump to the CWDM4 wavelength grid, which has a 20 nanometer spacing of each wavelength next to each other. I think it won't be sorted this year, and hopefully it will be sorted next year, that there will be a defined standard if it's either 20 nanometer spacing or 5 nanometer spacing. There are tensions to get towards CWDM4 because this technology having 20 nanometer spacing is way cheaper to produce compared to the LAN WDM. And at 100 gigabit, I was quite impressed seeing in 2019 that there are new things coming up, because it was somehow, it wasn't me, there was somehow a gap. The longest reach we could get was roughly 30 kilometers with ER4 light, and there was no movement ongoing in 100 gigabit. And in 2019, it happened that there came out solutions doing a pure ER4, doing 40 kilometers, or even ZR4 doing 80 kilometers in 100 gigabit. And when I'm talking about 100 gigabit, I'm talking about the interesting and nice form factors of QSFP28, not taking the CFP-X family in consideration, because I don't see them that much in the field any longer in typical layer 2, layer 3 switches or routers. So this is definitely an interesting technology. We do currently testing of those, and the performance looks pretty good. It also operates in the 1310 nanometer window, like mainly the maturity 100 gigabit technology. And the third one is, it's more like my personal view. I'm not quite sure if it will make it, but is the 50 gig Ethernet Why do I mention it? It's coming out of the 5G deployments. The 5G deployments, they have the need and the to connect their poles with high bandwidth, but they figured out, well, 50 gig Ethernet is enough for us, and 100 gig, for sure it depends on the design, how you build your 5G networks, for sure. But we don't need the 100 gig there because for us it's not necessary. And when you compare cost-wise, a 50 gig transceiver with a 100 gig transceiver, the 50 gig transceiver is way cheaper to produce and way cheaper at the end to use. And when you are a 5G mobile network operator and you have to connect a couple of thousand poles, then the cost per transceiver is something which you really take into manner, because you do not buy only one transceiver, you buy a couple of thousand or 10,000 pieces. And the other thing what I see at 50 gig Ethernet is the capability of the switches you have in place these days. Because the ASIC inside of the switch, he is able to handle 50 gig Ethernet. And looking at 400 gigabit switches, they will be able to do 400 gigabit, they can do 200, 100, 50, 40, 25, 10 gigabit, all in that one ASIC. That's pretty powerful. It all depends on the implementation of the operating system, how he drives the ASIC, and if it's able to, or if it does enable this type of technology. So 50 gig could be interesting, but it really depends on a couple of components there. Yeah. Finally, oops. In the single lambda environment, we see 40 gig, just one wavelength, without any amplification, doing LR distance, like 11 dB power budget, and also 25 gig, one single wavelength. No need to amplify there. This brings me to the end of the presentation. There is still a lot of freedom for us with the Flexbox to tweak all the parameters inside of the transceivers, and now with 400 gigabit, where we also have now a DSP inside, which also has a firmware which needs to be tweaked. This is going to be a new challenge also for us to change that configuration with the Flexbox. With the microcontroller so far, we are quite familiar, and now it's also adding the DSP there. We're getting there, and yeah, looking forward to it. Thank you very much for listening. One disclaimer here, all the toys are back to my kids, so no worries, I didn't take it. Thank you. If there are questions, I'm happy to take them.
Thank you, Thomas.
Thank you very much.
Thank you so much.